This is an example of a two-proportion hypotheses test. If there's time, we'll do a confidence interval. So let's look at the problem. It looks like this Employee Benefit Research Institute did a survey of people that are getting close to retirement, apparently, and asked them how do they feel about the money they've saved and their ability to live comfortably in retirement. So we see that the men, the percent of men that say they feel comfortable is 27%, and the sample size for the men was 250. But for the women, the sample that we get is 0.18, and the sample size for women was the same, 0.25. Okay, so there's definitely a difference, but the question is this a significant difference? Is it statistically significant? So before we get too far along, if I just multiply 0.27 times 250, I get 67.5, so that will become useful later on. And if I do 0.18 times 250, I get 45. So of the sample, these are the number of successes. So I know this is a half of a person, but we don't know which way to go, if it should be 68, if it was 68 or 67. So we're just going to leave it here. So before we go much further, let's ask ourselves, what's the objective of our test? What are we being asked to do? So I've noticed that they're asking us, is this strong evidence that men and women have different outlooks on their retirement? So if the true population is P for men, and for women it's PW, they're asking us to prove that they're not equal. They're asking us, is this strong evidence that they're not equal? So I believe that that's what we want to make as our alternative hypotheses. Okay? So with that in mind, let's see if I can do this. I have the author's hypotheses already written out. So using this notation where PM, subscript M, is the proportion of men that have a positive outlook, and PW, P subscript W, is the proportion of women, then we could write the proportion of those who anticipate having enough money to live comfortably in retirement is the same for men and women. And we repeat that, only we say they're not equal to. Okay, so those are our hypotheses, and we're going to try to prove the alternative. And the mechanism by which we're going to do that is see if the null hypotheses, it's going to imply a model, and then we're going to see if that leads to a false sort of statement. Okay? So let's see if we can do the conditions quickly. So random sample. Well, they didn't say it was random. If you notice, it looked like it was sounded like a pretty professional organization. So we're just going to have to assume the samples are representative. Sorry, this electronic pen is difficult to use sometimes. Of all people. Okay, something to that effect. 10%, so it should be 250 and 250 are both less than 10% of all people. Okay, independent samples condition. So I think it's safe to say that men and women are independent groups. No significant overlap, I hope. Okay, so now we'd have to do the success failure condition, so that's going to take a while. So n times p hat m is going to be 250 times 0.27, and that's equal to 67.5. We already did that. And then n times q hat m is 250 times 0.73, and that's 182.5. So we're looking good there. And then p hat w, that's going to be 250 times 0.18, and that's 45. And then n times q hat w equals 250 times 0.82, and that's 205. So all are greater than 10. So the samples are large enough. Okay? Okay, so since the conditions are satisfied, we will model the sampling distribution of the difference in proportions with the normal model. Okay, with a mean of 0, right? Because that's what we're hypothesizing right here, 0. So the center, according to the null, would be 0, and a standard error of, and then I believe we're going to have to pool, right? We're going to have to do p hat pooled. So first we do p hat pooled. So that's going to equal 67.5 plus 45 divided by, so it would be 250 plus 250. Okay, so that's, what is that? That's going to be 0.225. Alright, so now this big standard error that we need to calculate, I'm just going to say standard pooled, is equal to the square root. So the nice thing here is that once you have p hat pooled, it's the same for both terms, 225 times 0.775 divided by 250 plus, and it's the same thing. It just happens to be that the sample sizes are the same this time. So it's the same thing again over 250. All right, now you can do this. You don't have to put the parentheses in. You can do this in your calculator. Calculator understands order of operations. So I get 0.03735. Okay, so our model looks something like this. And we have 0 in the center, and our standard deviations, the standard deviation now we can kind of see is very small, 0.04 essentially. So this would be 0.04, so that's going to be 0.08 and 0.12, right? Counting by fours, that'd be minus 0.04 and minus 0.008 and minus 0.12. Okay, so now let's see. What we got to do is compare the observed value. So the observed difference, I'm going to call it. Well, that's going to be what? P hat M minus P hat W. So what were those values? They gave it to us, 0.27 minus 0.18. So 0.27 minus 0.18, and that's going to be 0.09. So let's see, 0.09. Well, that's going to be right in here somewhere. Okay, so our observed value equals 0.09. So let's see, how many standard deviations away is that? Well, that's going to be 0.09 minus the center of the model, which is 0, divided by the standard deviation, or the standard error, and that comes out to be 2.41. So that looks about right, right? 1, 2, and then a little bit more. Okay, so we're in, this is the p-value here. Would be this area under the curve. So let's see. So I'm just going to label this z.241. 241. Maybe I should have been over just a little bit more. Okay. So the p-value, that is the probability that the observed value p hat m minus p hat w is greater than 0.01 given that the center is at 0. So that's the same as the probability of z being greater than 2.41. Okay, so that's normal CDF of 2.41 out to infinity. Okay, and what I get is, oh, hold on, hold your horses. We have a two-tail test because we said not equal to. So that implies two-tail. Okay, so we have to double this. We have to include this. So we have to put I think we have to put a 2 there, and a 2 here, and a 2 here. Okay, so that comes out to be 0.0160. So pretty small. So the p-value is approximately 1.6% of the time. All right, so since the p-value is small, we reject the null hypotheses. All right, so there is strong evidence, using their words, strong evidence of a difference in the proportion of those who anticipate having enough money to live comfortably. In retirement. For men and women. Now let's see if we can go a little bit further. In fact, the evidence suggests that a greater proportion of men feel comfortable about retirement. Okay, so I'm going to stop here and do another video for the confidence interval. But so this just kind of leads in to the confidence interval. But the idea here is that we expected to get a value closer to 0, and it's much further away. And so that's inconsistent with the model, which means it's inconsistent with the null hypotheses because it implies the model. So we kind of have a contradiction. I don't know about a false statement, but a contradiction. So that's why we accept the alternative. Okay.